Hello, sorry for the delay. Hello, hello. Okay, hold on. Sorry for sorry for the lateness. Hold on. Coming. Oh, yes, good afternoon. Good afternoon. Thank you for your patience. Sorry about that. Coming on. Right. Yes, good afternoon. Okay. Okay. Good afternoon. Good afternoon, Vicky. Good afternoon, Raina. Good afternoon, Caitlin. I apologize for this crazy start. Good afternoon. Yes, good afternoon. Ethan. For this crazy start. Okay. Uh,
Good afternoon, Professor.
Good afternoon, Lear. Good afternoon. Thank you. Sorry about and good afternoon, Andre. Uh, and Roger. Sorry for this delayed and crazy start. We will get I s- we'll get settled and start in a second. Okay. Um. Okay. Gonna wait another minute because I ran late and I don't know if you guys I sent the notification saying we're not gonna start for we're gonna start 10 minutes late, so I'm gonna wait a second for the other. Well, actually, I'll say this quickly. Do any of you guys who are here right now, do you have any? I mean, I'm gonna pick up from where we were yesterday, but do you have any questions you want to ask at all from yesterday, from the physics or anything before we get any of you who's here right now? I mean, if not, that's fine. But just gonna wait. Okay. Well, okay. If um, okay. Um, I'm gonna start in 1 second. Oh, actually, yes, I'm gonna start in 1 second. Okay, I know there's people in the waiting room. I'll get them, and then we will get right to it. Okay. Many people in the waiting room. Okay. Okay.
Good morning. Good evening, Professor, or
Good
afternoon.
evening.
Sorry.
Good day. Happy day. Yes, thank you. I appreciate it. And hello. Hello. Okay. Thank you. And thank you for your patience, guys. Sorry about this late start and all the craziness this week. A good morning, and afternoon and day, Melanie. Good afternoon, Victoria. Okay. And here's a, so I'm just gonna, I know we've already lost some time, so I'm going to just get to it. Um, well. I'm just going to get to it. In fact, the easiest way, I want to pick up from where we were yesterday. I mean, yesterday we had a big conclusion, a big physics conclusion. Um, that's sort of going to frame our topics for the much of the semester. Um, the, so there's still much more to be said about it, and I want to summarize and review and reflect. But the easiest way, really, to summarize, to emphasize, to drive in the conclusion that we got yesterday, the easiest, most direct way, especially right at this moment, is to go straight to homework two. And while homework two is helping us practice what we concluded yesterday. So that's what we're going to do. Now, again, I mean, so good afternoon, Victoria and Sonam and Aminata and Kyan and Gabriel and Zoe and Joel and Anthony. You didn't miss anything. I mean, thank you for your patience. We just started. I did start class late. I think you got the message. I guess right. So you didn't miss anything. I'm going to start, but I apologize to everybody. But I'm going to start now. And hello, Anthony. Um, I'm going to start now. Hold on. And well, yeah, I'm going to start now. This right here on the board, right here. Well, actually, okay. This more or less is what we concluded yesterday, more or less. But you may notice, and we're going to practice this and see what it all means. We're going to practice this right now with the homework number two. Just notice one little subtle thing. Yesterday, those were all X's on the board. Now they are Z's. What is that? That's not a typo. Does it make a difference? Well, yes and no. Yesterday they were X's because yesterday we were specifically analyzing the physics of a spring, of a mass on a spring. We were specifically analyzing what could be said about the position along a one-dimensional line, like the position in meters of a mass on a spring with a certain stiffness. Um, and using physics, using Hooke's law and Newton's second law and the definition of instantaneous acceleration, we realized, oh, this mass spring behavior can be best described by a differential equation. And we needed to solve that differential equation in order to get a space-time function, a position-time function, right? So I am summarizing a little bit. So all the work we did yesterday was to take the differential equation d2x dt squared equals negative k over mx. We took that differential equation and we found a solution to it. And we said a solution doesn't mean a number. A solution means an equation which takes in t as the independent variable and spits out x as the dependent variable. That's what we were looking for. That's what we got. And what we got was x equals x naught cosine omega t, for which omega meant or stood for or equal to square root of k over m. Now, again, this is a quick summary of what we did yesterday. Believe me, even if it went faster, even if I'm going fast now, you're going to see it again and again. But the summary that I'm trying to say right now is we applied some physics laws to a physics situation, to a specific physics situation, and out came a mathematical expression called a differential equation. We then did the math, or we got a solution to that differential equation and used the solution to predict the specific position of this specific mass on a specific spring. Now, what I want to say before we go any further, what it's saying on the board, why I changed the X's to Z's is not to confuse you, nor it's not meant to confuse you, nor is it a mistake. The reason I've changed the X's to Z's is from here on in, I want to emphasize that the math we did yesterday, the math that we saw, differential equation, the math we considered, finding a solution, checking the solution. That is true in general. X didn't have to be X. It didn't specifically have to be meters on a line for a mass going back and forth. It could be X could have been any measurable dependent variable at all, such as it could have stood for angular position of a pendulum. It could have stood for uh, current going back and forth in an electrical circuit. It could have stood for temperature in a certain kind of like weather system or thermal system. What we realized, the reason we spent weeks building up to this, and the reason it's such a big deal, is what we found yesterday is that for any situation that differential equation applies, then that type of cosine solution, that type of cosine expression will be a solution. So we have now discovered something that's sort of generally true for any system in the world that behaves like a mass on a spring. It's not just true for masses on springs. It's true for any system that has the same mathematical properties as a mass on a spring. So, okay, so what I'm saying is, first of all, I'm saying, uh, yeah, okay. And this whole thing, okay. From now on, I'm saying Z could mean any measure time dependent measurable variable or any measurable time dependent variable. So Z is any dependent variable, any variable that depends on time, right? T is still time. This whole thing that's written on the board here is the mathematical description of what we're from now on going to call SHO, simple harmonic oscillation. And that's really the topic that we're studying here. Like if you wanted to look this up in the optional textbook or in a Khan Academy lecture or something, what we're studying here is called harmonic oscillation. A harmonic oscillation or a harmonic oscillator is any system that behaves like an ideal mass or a mass on an ideal spring. Anything that we said in homework one, questions 1 through 8, any of those things we discover going back and forth forever, having a maximum speed in the middle, having a maximum potential energy at the edges, any of these properties, conserving energy, all those things are characteristics of any system that acts like that, including like a simple pendulum, say lab 2, right? Or certain electrical circuits, anything that acts like a mass on a spring is known as a simple harmonic oscillator. And specifically, I mean, we're going to talk more and more about this. So a harmonic oscillator, and you do want to write, I don't have room to write that with it. Well, I will write it. Hold on a second. Okay. Okay. So I'm gonna translate. No, no, and thank you for the apology. No, I was late. I mean, chat person. I mean, thank you, but I was late. Um, uh, okay, and again, this is all meant to slightly recap, or this is trying to emphasize the big conclusion that we came to yesterday. Like yesterday, we did a lot of kind of unusual math. We're we're going to need that math for the rest of our lives. We're going to redo it sometimes. We're not going to always redo it, but we need it. What was it about? It was about a system. It was about a mass on a spring, but now we're starting to say, look, anything that behaves like a mass on a spring is what we're really talking about here in physics. Oh, and by the way, I keep saying like mass on a spring or simple pendulum or certain kind of circuits. I mean, that's all definitely true. But even more important for those of you going on in this major or going on in STEM, this whole idea of a simple harmonic oscillator also very much describes uh, quantum systems, atomic systems, like which you'll study in depth at the beginning of PChem, which most of you will take next, right? I mean, so this happens. So this idea of a system going back and forth, cycling, like repeating a certain behavior over and over and over again in a cycle, is a very important idea in nature, microscopically and macroscopically. Anything that cycles in a certain kind of precise way, we understand by taking the same math that applies to masses on springs, like the way we understand quantum harmonic oscillators. Again, the beginning of PChem is that we say that they act like little masses on little springs. And what does it mean to act like a mass on a spring? Well, in mathematical terms, it means to obey Hooke's law. It means to continually be subject to a restoring force, restoring force that's pulling you back toward equilibrium with a strength that is directly proportional to your displacement from equilibrium, right? That's what Hooke's law is. Anything that is a simple harmonic oscillator will obey a version of Hooke's law and vice versa. And Hooke's law, once we express it in general mathematical terms, is that differential equation that I'm going to keep writing over and over again. That thing that looks intimidating, d2z over dt squared, or like yesterday, d2x over dt squared equals negative constant times the z or times the x or whatever. That we're going to get more and more used to that. But what that really is just Hooke's law. We got there by just saying, just substituting Hooke's law into F net equals ma, and then remembering that a is defined to be the second derivative of position with respect to time. So what I'm saying is, first of all, I'm saying to be an oscillator of this kind is to obey this mathematical expression of what really in the end is Hooke's law. But I'm also now going to say something that's a little bit more specific, and then I will apply this to homework two. Notice that the solution to this kind of equation, the solution that we got yesterday, x equals x naught cosine omega t. Today I'm saying it more generally. It doesn't have to be x, it doesn't have to be y, it doesn't have to be theta, it doesn't have to be I, it could be anything. So I'm just calling it z, right? What this is saying here, well, I guess I'll say this more and more later, but what this is saying here is getting at, what do I mean by harmonic? I mean, are all systems that oscillate, is any system that cycles back and forth in some kind of a way, is it necessarily a harmonic oscillator? And the answer is no. To oscillate, so harmonic oscillation is very special oscillation, and that's the kind that we're looking at now. Oscillation just means cyclical behavior, behavior that repeats itself over and over again. But that could be very irregular. It could be like me walking back and forth at the front of the room and taking a certain amount of time to go one way and then a different amount of time to go the other way. Right? Oscillation just means cyclical or periodic behavior. But harmonic oscillation, which is what we are now talking about here, means that the rate at which the system goes back and forth, the rate at which the system goes back and forth, the number of cycles it makes per second, let's say, is number one, a constant, and that's really important. For a harmonic oscillator, the rate at which something goes, the rate at which the system cycles is a constant. And that constant is what we call omega. That's what this omega is. We'll see more and more today and next week. This term right here is the rate at which the cosine graph goes up and down, or the rate at which the mass makes round trips per unit time. That's what omega really is. Remember, we didn't know what omega was when we started. It was just a placeholder. But what it was a placeholder, why? How did we know it had to be there? Because we knew there had to be something next to the t that was measured, some kind of constant next to the t that had to be measured in radians per second. Radians per second is a rate. It's the rate at which we're carving, like it's the rate at which the cosine graph would wiggle back and forth per unit um along per each unit along the x-axis, right? We're going to talk about it more, but omega, the radians per second, is ultimately an indication of how rapidly or frequently the system completes cycles. What we're saying is that a harmonic oscillator, the kind that we are now dealing with, is an oscillator that maintains a constant rate of cycling per second. And that rate is so constant, that not only doesn't it change in time, but it doesn't even depend on amplitude. It doesn't even depend on space. What do I mean by that? And then I will move on. I'm just trying to observe. No, if when we said yesterday, when we said that the solution to the differential equation was x equals x naught cosine omega t, right? And then we plugged in numbers for t and for omega and for x naught so that it spat out an x. If you notice that omega in there, we said yesterday, omega equals square root of k over m. That omega, so it depended. It depended on k and m, but it didn't depend in any way on z naught. The omega that we plugged in as the rate of radians per second was not at all determined by how far out the mass was initially held. So the amount of time, so therefore I'm saying, and then I'll move on, I'm saying the rate at which the mass went back and forth did not depend on how far back the mass was initially stretched. That's how constant its rate of going back and forth was. It wasn't just constant, it was independent of the initial displacement. That, and how do I know? Again, because the omega has nothing to do with the z naught. I mean, the omega we found yesterday equaled square root of k over m. It didn't equal z square root of z naught over m or something like that. And now again, I'll say this more a little bit later, but what I'm trying to say now is we are now studying harmonic oscillation from here on in. Simple harmonic oscillation. From here on in, simple harmonic oscillation means cyclical behavior, like behavior of a mass on a spring, for which the cycling rate doesn't even depend on the cycling size. That's what I'm ultimately trying to say. That's a big deal. That is what it means to be a harmonic oscillator. And you will only be a harmonic oscillator if you are being governed by Hooke's law. Okay, that's a summary of what I'm saying right now. Okay, that's like a lot of abstraction. So So it covers like a lot of nature. Hence, we spend a lot of time on it. Hence, we're now going to practice the mathematics of it in homework two. So I'm going to move on now and start going over homework two. Thank you for your patience. Hold on. Okay. And like usual, oh well, oh yeah, wait, sorry. And there's a thing in the hold on. Wait, okay, so two things. Well, there's a thing in the chat. Hold on. Okay. Yeah, yeah, absolutely. So in the chat, so we're still getting used to this. Or I guess, and some people are newer to this class than others. Yes, absolutely. If homework, the advantage of handing in your first draft of homework on time, the advantage of handing it on time, it means that when I eventually give feedback or whatever, it means that you could eventually get all the points on homework. If you hand in your first draft of homework on time, and it's always a draft, it means that even if you don't get all the points, or even if you made mistakes or things are incomplete, you can eventually keep revising it until you get all the points for the homework. And those revisions could come later. That's if you hand it in the first draft on time. If I'm just answering a question in the chat here about late homework, if you hand in homework late, if you hand in your first draft late, oh, I will definitely still grade it. I might not give as much feedback, like I'm always a little bit behind, but you'll definitely get credit for it. Let me be super clear, especially for people that never had me before. If you hand in your first draft of a homework like a few days late, you will definitely get credit. It's just the one difference is you may not get all the credit. I mean, you probably won't get all the credit, but you'll get most. You will certainly get enough. Like you just won't be able to revise and upload until perfection, the way that people that would hand in their homework, um, their first draft promptly do. So I hope that's clear. And if it's not clear, please let me know again. But what I'm trying to say to everybody is, I will take off just enough to hopefully encourage you to stay on top of your homework and hand in rough drafts. Like basically, if you hand in a rough draft on time, then you have that much more time and possibility of revising until perfection. And you can benefit from the class lectures and so forth. But if you hand it in late, you're still going to get enough points that I'm trying to tell you it's still totally worth it. It is still totally worth it for you and for me to do your homework, even if it's late, and, as practice for the exam and all that. So you'll get a ton of points. And also, I won't like be shaming you or anything about it like but you just can't get all the points. And obviously then if it gets super late and it gets more and more, it gets less and less worth it the later it gets. But I hope that's clear. um yeah, I hope that's clear. Oh, got it. Thank you. Okay, great, thank you. Okay. And that's closing a conversational loop, so you get points for that. That's good. All right, so we're going to go over homework two now. Now, what I'm going to do is the same thing I did with homework one, with just like the first exercise. I'm a little bit going to beat it to death. I apologize. Like I'm going to do the 5-step method and everything of what I was looking for, so you could see. But then, then I'll kind of race through the exercises after that as we get. But so for the first one, hold on, so I'm going to screen share. Oh yeah, so I'm going to do a quick screen share. Okay, so this is what we're talking about, right? Whoop. Okay, hold on. Okay, this is what we're talking about, and I'm going to prepare my other screen while we're doing that. Hold on one second. I know you can't see what I'm doing or hear me yet. Just give me a second. But the first question is what we're doing. And someone's here. Okay, hold on one second. Okay, I'm going to let the person in. I'm going to switch screens and okay. One quick thing. So I'm going to switch screens back, but so this first question, derivatives, A, given x equals A cosine omega t, find dx dt and you know that. Notice, and then it says B. What's happening here? Like I mentioned yesterday, this is doing the same thing we did in class yesterday. Only this is going backwards from what we did yesterday. And that's kind of interesting because yesterday, if it felt weird what we were doing, it might have felt weird because what we were doing yesterday actually is kind of backwards. And this is the backwards of the backwards, i.e., this is the forwards. What am I saying? I am saying that in physics, that we stumbled on a differential equation when we saw Hooke's law in action, and a differential equation is looking for a solution. And you notice yesterday the way we got that solution, we didn't just do a straightforward procedure. We didn't just follow some rules that we were supposed to already know or something like that. We had to do this kind of funny guess and check thing. That's what we did yesterday. And we guessed a solution and then we checked that it was right and it was right. And many of you may, if you've never seen this before, you might be thinking that doesn't really seem like math, or that doesn't really seem like scientifically valid. Like, is that the way a real math person would do it? Is that the way a real? And the funny thing is, yes. I mean, honestly, a real math person or a real science person, if they were really used to this, if they had been working with harmonic oscillators for a long time, they would just already know the solution. So they wouldn't go through all that. But solving differential equation, if you ever noticed when you took calculus classes, when you take derivatives, you move forward. Like someone gives you, maybe it's hard, maybe it's easy, but somebody gives you a function on an exam and they say, take the derivatives of this. Like if you know the rules and you know what rules apply, like if you know, oh, I have to do chain rule, or oh, I have to do product rule, or something like this, or maybe a bunch of rules. If you know the rules, you just apply the rules and you get a derivative, right? But in contrast, integrals are not quite like that. If you ever notice, integrals, you're kind of working backwards. You're more like hoping that you remember the correct technique and you're like solving a puzzle kind of, and the puzzle either works or it doesn't, if you know what I mean. And that yesterday is more like that. We're doing derivatives backwards yesterday. We're trying to fit where it's like a puzzle. There might be an answer, there might not. It's not a clear path. And that's the way it is. That's why differential equations are tricky. What today, what today in this homework is trying to do, it's trying to say, let's think about this more clearly. Like, what did we do at the end yesterday after we guessed the solution? We checked it. We checked to see if it was a solution. So let's pretend we're in that space now, is what it's saying. Let's pretend someone's already proposed a solution and let's check whether it works or not for a differential equation. So I'm going back, switching screens again. Okay. So if I were doing the homework, if you were doing the homework, okay, here's first of all my diagram and fact pattern of the very first, like it said, given x equals a cosine omega t. So here's my diagram. And I think I warned many of you that, we do look for a diagram, especially when no one provided one for us. So my diagram is like a cosine graph, right? And what does it mean to do a graph in physics? It means really three key things. One, a shape or a simple shape or trend. In this case, the simple shape or trend of the cosine curve. Two, fully labeled axes. Okay, fully labeled, I should say. Labeled axes so we know what the shape is, what relation the shape is representing, and at least one key value to show the scale of the graph. So I have my key value here is x naught is, I'm sorry, what they're calling in this problem A. Talk about that in a second. Okay, so I've labeled the point A. It's the y-intercept. And then I've labeled one other thing in my graph, the more subtle thing. I wouldn't necessarily put this in every single graph, but I'm definitely putting it in the graph of this problem because remember, when you're doing a physics problem, The main purpose of putting a diagram is that every single constant or variable that you're going to be using in your step 4 in the math that you do, in the computations that you do to solve, every single letter needs to be defined before you use that letter. And the way to define letters, the way to define constants and variables is by making them labels in a diagram. So I try to use this diagram, in other words, also to show what I mean by omega. Like the diagram is trying to show what we mean, like basically everything. X is an axis, the dependent axis. T is an axis, the independent axis. And omega and A are constants that I'm trying to make clear what they mean in the picture. So for example, so A, the easier one for the simpler one first. By A, what I mean by definition, what A is the value of X when time is 0, right? In other words, what A is what we've been calling X naught. Now, why am I introducing a new, like, why don't we just call it X naught then? Right. But that's what it is, right? And you see that on the graph. Like, literally, it's where the graph crosses the y axis. It's the very initial value of X. Now, but why am I changing names? Like we called it X naught for weeks. Why are we calling it A now? Well, it's just now that we're thinking of this system as an oscillator, there's a subtle distinction. I mean, it's just a distinction of emphasis. But when we use the term X naught, what we're really trying to emphasize is that the value is the initial starting value. But from here on in, when we use the term A, which stands for amplitude, we're trying to emphasize that it's the maximum value. Now, they are one and the same. This is like another triple equal sign versus double equal sign thing. I'm saying, like, do the mass on the spring. The mass started at a value of 0.15 meters from display, 0.15 meters from equilibrium. That's where it started, so we call it X naught. But then we answered a bunch of questions and we realized, well, that's not just where it started. That's as far as it's ever going to get because it conserves energy. That's where it has zero kinetic energy, maximum potential energy. So it's going to go back and forth between 0.15 and negative 0.15 meters. So 0.15 we could think of as X naught, but then we realize it's not just that. It's a turning point or an end point or like a maximum boundary on this oscillation. So from here on in, the boundary on your oscillation, the maximum space, well, the maximum value that the dependent variable will ever achieve from now on, we call amplitude. Which I mean, I know most of you know that word from high school or from seventh grade, but I'm just trying to be clear now. So we're going to use A or X naught or Z naught. We're going to use all these letters interchangeably. They don't literally emphasize the same idea. One emphasizes beginning, another emphasizes maximum, but they all turn out to refer to the same thing when you're talking about an oscillating system. Okay, so A is there in the diagram. It's labeled as the value of X when T equals 0. Now, but then there's this omega thing. Now, omega is a big deal. Omega, now I know we found out yesterday that omega equals square root of k over m, and I have a lot more to say about that. But that's a double equal sign. That's what it turned out to equal, square root of k over m. In the first place, what? Like, what does it mean? Where did it come from? Okay, hold on. Okay, so what is this omega thing? Like, first, it was just an art, it's a Greek letter. It's a lowercase Greek letter. When we introduced it yesterday, all we knew about it We put it there because we knew there had to be some constant whose units were radians per second, right? I mean, that's all we knew yesterday, that there had to be so it's some number that doesn't change that's measured in radians per second to cancel out the seconds of t and leave us with radians that we could take a cosine. Well, I mean, why are radians coming in to our life when we're talking about a mass going straight back and forth on on a horizontal line? Here's why. Okay, radians are a unit of measurement for an angle. The question is, why are angles suddenly coming into this? And you might even say, well, because cosines are coming in. Yes, that is true because cosines are coming in, but still, how is it that we're allowed to talk about cosines and angles when we're talking about something going straight back and forth? Well, here's why. So this is all an instructor sidebar. I'm explaining something now. I'm not saying you have to do all this in your homework. I am saying in your homework you have to label omega in that graph, but now I'm trying to explain to you what that label would mean. I'm saying first and foremost, in a big way, I'm saying what is an angle? An angle, sure, an angle can be captured, can be pictured in your mind as like something like this, right? I mean, whenever I think of an angle, I think of something like that. But don't be fooled the way I was. Don't get thrown. An angle is not the distance between two intersecting line segments or between two arrows. I mean, it can be pictured that way, but that's not what it is. An angle is not how far one of my hands is from the other hand. It's obviously not how far it is because we already have that concept. That's called distance, right? It's not like if I put a ruler between my two hands and measured that length, I would have an angle measurement. No, I would just have a length measurement. So what is it? What do we mean when we say this is a bigger angle than that? What we actually mean, what an angle actually is a fraction of a circle. Like literally, even when I go like this, what I'm asking you to picture is some section, some chunk, some slice of a circle, like how big a certain slice of pizza is taken from a whole pie of pizza, right? In other words, and let's be really clear about this. Everybody can recognize 90 degrees, whether you call it 90 degrees or you call it pi over 2 radians or you call it a right angle. What a right angle is, if you think about it, is a quarter of a circle, right? No matter, right? I mean, that's what we're recognizing. If you really, I mean, everybody can recognize the two, like it's a vertical line and it's a horizontal, like everybody knows what a right angle is, but it's very hard to describe. Like they're like straight, right? I mean, they're not bent. What you're trying to say when you say, I know what a right angle is, you're saying that is literally a quarter of a circle, right? And what you really mean when you say it's a quarter of a circle, what you really mean, I think, what I really mean is, I don't care how big the circle is. I don't care if you measure from my fingertips to my other fingertips, or you measure from my knuckle to my other knuckle, right? Or if it's your hands and your hands are a lot bigger than my hands are, it doesn't matter. I can recognize that this is a fourth of a circle, no matter how big that circle is, right? Much in the same way that my 10-year-old son absolutely no 10-year-old son who's clearly not well, he's not taking trigonometry or calculus or anything like that, doesn't care about any of this stuff, but he knows what a 360 no scope is in Fortnite, which you may or may not know. He knows what a 360 is. I'm saying he knows a 360 is a full circle. That's how he thinks of it and how you think of it, right? He doesn't think of it as an angle, but he knows it's 360 is a full circle. So he knows, I mean, I've seen him do, so he knows if you do a half circle, it's 180, right? So he's thinking in terms of circle chunks, and I'm not saying he's getting involved in all the details, but that's what we want to do when we think of angles. In fact, specifically, you may recall, right, when you're measuring in radians, an angle is arc length divided by radius, right? Now, at first, many of us just sort of memorize that or accept it, but think about it for a second, what we're saying. When we say that an angle is arc length per radius, I'm going to write over here. Look at the units. Arc length is measured in meters, radius is measured in meters. We're saying it's some kind of ratio of meters to meters. The meters cancel out. It's a pure fraction. What theta is. What we're saying is when you say that theta is arc length per radius, you're really just saying theta, an angle, is how much of the circle you're taking up, like how much arc length. But then we're dividing by radius because we want to normalize ourselves. We want to correct ourselves. We want to say, if I have twice as much arc length as you, right? I mean, so in other words, half of a circle is twice as big of an angle as a quarter of a circle. That's what we're trying to say. But we wouldn't want to accidentally fool ourselves if I had an arc length that was twice as big as your arc length, but not because I went halfway around the circle, but only because I chopped my arc out of a circle that happened to be twice as big as yours. If my radius was twice as big as yours, we wouldn't want that to lead me to believe that I had taken a bigger angle than yours. So we always divide by the radius. So what we're really asking when we ask what an angle is, we're always just saying the amount of arc length you get per each one unit of radius. So as though we were all measuring. It's a way of saying it doesn't matter what circle you pick. We're asking how much arc you get for each one unit of radius of that circle. So a quarter, right? For example, then, if you go around the whole circle, if you go a full circle, as you know, but I'm just reminding you, if you go a full circle, you go around the entire circumference. That's the entire circumference of any circle is 2 pi r. Then divide by the radius of that circle. If you go around a whole circle, we call that 2 pi radians, right? Right? A full circle is 2 pi radians. A half a circle is pi radians. A quarter of a circle is pi over 2 radians. Why am I getting in the weeds of this? What does this have to do with anything? Well, it has everything to do with what we mean by omega. Omega is measuring radians per second. Omega is measuring radians per second. What is a radian? A radian is a sixth, approximately, a sixth of a circle. What? Where'd I get six from? Six is approximately 2 pi. I'm saying this, and then I'll get back to I'm saying this. First of all, I'm saying if first of all, I'm saying since we're going to be doing everything's going to be in radians from here on in, just as a public service reminder, in the end of the day, I mean, most of us are used to degrees. We're not used to radians, but that's the only difference. We're used to degrees. We're not used to radians, but that doesn't mean that degrees actually make more sense. If you start just thinking of if you think always there's 2 pi radians to if you remember that angles are chunks of circles, no matter what, that really a degree is a 3/60th of a circle, right? If you're always thinking in chunk fractions of circles, then then there's then a radian is the thing for which 2 pi of it makes up a circle. There's 2 pi, exactly 2 pi radians in a circle, but 2 pi is like 6.28, right? So that's approximately six. Approximately, just so you can picture it. Picture, I'm not lying to you, I'm just saying, be approximate for a minute so you can have a feel for what's going on. 2 pi is approximately six. Therefore, there's approximately six radians in a circle. A radian is approximately 60 degrees. It's a little bit less. It's like 57 degrees. But approximately a radian is just a 60-degree angle. It's just a sixth of a circle. Why? But the key of it is it's a sixth of a circle, regardless of how big the circle is. Because that's the whole nature of pi. Pi means, I don't care whether the number is 3.14 or 3. I mean, yes, it has all these special properties, but the first foremost idea of pi is that it's saying, I don't care how big your circle is. Go to any tree in the forest, take a piece of string, wrap it around the tree, put the string down on the ground. Now cut straight across the tree, put a string straight across that tree, put that string down on the ground. It doesn't matter what tree you picked. It doesn't matter how big the circle is. The first string is pi times bigger than the second string, like a little bit more than 3 times bigger than the second string for all circles. That's the discovery of pi, that it's constant for. So what does all this have to do with masses on springs and all of that? What it has to do with is a radian. A radian is then a section of a cycle that is independent of how big the cycle is. That's what we're saying. So we're saying well, in other words, wait, I'm just looking at there's a lot going on in the chat. I'm sorry. Wait, what? Oh, oh my God. Okay, I don't even know what's going on in the chat. I'll just make the safe choice and ignore the chat for the moment. But hopefully this is making sense. Hopefully this isn't too. Okay, so what I'm saying is, if you go back to my picture, I'll go back to the homework now. But look, well, actually, wait, let me write one more thing, and then I'll go back to the homework. I'm saying, what do radians have to do with oscillating systems, systems that are going back and forth? What radians have to do with them is that in the end of the day, a radian is a sixth of a cycle. A sixth, not exactly a sixth. If you want to be exact, you could say it's a 2 pith of a cycle. But if you want to get a feel for what's going on, I'm saying I'm saying to measure radians per second, which is what omega measures, to measure radians per second is to measure the what is to measure angular frequency, which sounds like a very, I mean, that's what it's called. Omega stands for what is called angular frequency. That sounds like a very strange thing to apply to something that's going back and forth in a straight line. But it's not a strange thing to apply to something going back and forth in a straight line if you think of angles as sections or portions, fractions of cycles. A radian is a measurement of angle. An angle, 1 radian, is like a sixth of a cycle, like literally. So when we measure angular frequency, we're measuring how rapidly this thing goes back and forth. Only we're sort of off by a factor of 2 pi, or we're off by a factor of 6 from what would be a natural physical way of counting. So we say this. So I'm saying this. I'm saying I'm saying if I walked up to you and said, this mass on the spring has an omega has an omega of 2 pi radians per second, if I said it has a omega of 2 pi radians per second, has an angular frequency of 2 pi radians per second, that even to me, that sounds like a very strange thing to say. But what it means is, since there's 2 pi radians for every cycle, it means that this system is completing 1 cycle per second. In other words, if you ever want to convert in your mind from angular frequency measured in radians per second to the more common standard frequency measured in cycles per second, or what we call hertz, you could just say, oh, F standard frequency is always equal to omega divided by 2 pi. Because the key point is that there's 2 pi radians for every cycle. I'm going to take it one step further, and then I'll be, uh, if capital T stands for period, like you measure in the lab, if capital T stands for period, or amount of time for 1 cycle, so if the units of T are not radians per second nor cycles per second, but rather seconds per cycle, if T is how many seconds there are in a given cycle, then T is the reciprocal of F, which means it's right. I mean, literally, if you know for a fact you're doing 2 cycles every second, that means you're taking 1/2 of a second to do a cycle, right? You may want to like think this over in your mind, but what I'm old, right? So I'm going to do this. I mean, if we had more time, I would like literally make this a class exercise right now, but I'm going to say, well, I'm going to summarize. Hold on 1 second. Okay, I know we only have 7 minutes left. I'm just trying to say, and then I will go back to the first homework. This is all me talking to you. Sorry, I'm ultimately trying to say, if you know one of these three, these are three distinct ways of describing the rate at which something cycles. This is cycling rate for an oscillator. If you know, there are three different ways to talk about it, but if you know one, you automatically know the other two. They're all relatable to each other. Why do we have three different ways? Because omega comes directly from the math. Omega radians per second, angular frequency, is the most direct way to speak about things mathematically. Period, capital T, is the most, for all of us, the easiest way to picture things and the easiest way to measure things in the lab. So on the one hand, you have radians per second, and all the way on the other end, you have seconds per cycle. The bridge between the two is standard frequency, cycles per second. That helps you transition from one to the other. Um, but if you understand one, you can always get the other two, right? And the whole bottom line of this whole thing, and I know we're running out of time. The whole bottom line behind this whole thing, the anchor is we're now talking about oscillating systems going back and forth and back and forth. So from here on in, we don't care how big their cycle is or what kind of system it is. The one thing we could talk about is how rapidly they cycle. And the way we talk about how rapidly they cycle, or at least the way we mathematically analyze how rapidly they cycle, is we do it in terms of radians. And whenever in doubt, whenever you're lost, always go back to the idea that a rate that 2 pi radians makes a full cycle. Hence my picture here. So I know we have very little, I'm just gonna finish one exercise, but hence my picture here when I'm doing the math. Now I'm not, again, did I expect you to write all of that for me? No, 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 no. Do I even think that you understood all this? Some of you, I think, understood all of that already in your own way. I'm putting it my way now. Some of you didn't. But what I am trying to say is in a cosine graph from here on in, what I am saying is in a cosine graph, what is omega? Omega is omega is like the reciprocal of period. Period is how much time it takes to get from one peak to the next on a cosine graph, or how much time it takes from the mass to get from one spot all the way away and back to that spot. That's what capital T is. So omega is like the reciprocal of that, but converted by a factor of 2 pi because there's 2 pi radians for every cycle. Okay, so that's what omega is. Literally, it's 2 pi over that period. That's my graph. Now I know, again, that was like a big, but that's what omega means. So you notice, so in a harmonic oscillator, omega, radians per second, is how rapidly the oscillator is oscillating. What we found out yesterday is that in the case of a mass on a spring, that rate is determined by the square root of k over m. It's determined by that. But what it means is this rate of oscillation. So very quickly, with the 4 minutes that we have left, just so I can at least complete one problem with you. Obviously, we'll pick up on here next week. The problem, yeah, we 3 minutes. So the question. So I've done step one. I've done step two. No, I've done step one. So now step two, just really quick. Step two is A1. What is the first derivative of this function, right? Well, okay, I'm going to do this again. Again, I'm doing this a little more quickly than yeah. How would I do this? If I'm doing the homework, I will do this correct. This will be a few minutes. Step three, I would say, first of all, in general, because this is step three, right? I'm writing general things. In general, if y equals cosine of x, like in math, then the derivative equals negative sine of x. That's a general statement from math, right? But also in general, I would say if y equals some function of x and z equals some other function of y, if you have a function of a function, then what's true is that the full derivative of the entire thing equals the outer derivative times the inner derivative, right? That's called the chain rule, as many of you are aware. And when you write the chain rule, and now you may have to think about this at home, but when I write it like that, suddenly, at least to me, the chain rule makes sense. You may never have seen it written that way before, but think about it at home. If you have a function of a function, then the full function derivative is the outer function derivative times the inner function derivative because the dy's cancel like that. So I would write that down. So in other words, we have chain rule and we have trigonometric derivative. I know we have 2 minutes left. So now I can go to step 4. I can go to step 4 and say, therefore, here, then, if I apply both of those rules, then dx dt will equal negative a sine of omega t, but times omega, right, by the chain rule. So the omega will come out. I'm looking at the time. We have 1 more minute, right? So that's the first derivative. And so that's the answer, in fact. Right? That's the answer. We have 1 more minute. Don't leave yet. We have 1 minute. So that's the answer, step 5. But then just so that we can finish this, in part 2, they ask to do the derivative again, the second derivative. So if I do it again, I get just like yesterday, I get negative a omega squared cosine omega t. And so then in B, I'll pick up from here next Monday, but B where it says, is x equals a cosine omega t a solution to blah, 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 blah? The answer is yes. It is yes, because, and we're ending right now, I promise. It is a solution because it would have been easier if I because if I had written it that way, because this part right here is x. So so the second derivative of x does equal x times omega squared times -1. So it is. Yeah, okay, that's it. Okay, thank you for being so patient. We'll pick up with it. So just keep going wherever you are in the homework, and I'll see you Monday. Thank you. And
Professor, the next homework, homework 3 is not due on Monday then, right?
I believe, wait, let me see. Give me one second. Hold on, I'm going to stop. That's a